Hi, welcome to this fourth introductory video where we will see the third of the three types of geometry. The first two types we saw in the previous video. The first being the ancient knowledge of geometry collected, organized, proved and published to the world by Euclid in his book Elements in the 2nd century BC. The second was centuries later in the 17th century AD when René Descartes combined algebra and geometry. We noted that this system led to advances in trigonometry and calculus. But in geometry itself, there were no major developments until the 19th century AD when Carl Friedrich Gauss and a few others began questioning diligently whether there was any geometry different from Euclid's. To answer this, they began examining Euclid's system of proving the characteristics of shapes, as seen in the second introductory video. First, state obvious truths. Next, use obvious truths to prove simple characteristics of shapes. And then, use obvious truths plus proven simple characteristics to prove advanced characteristics of shapes. Now notice that all of Euclid's geometry depended on what was taken as obvious truths, because all his logical proving thereafter was based on them. So, if the obvious truths were not truths in a different situation, then there should be a different geometry for the different situation. To understand this, let us consider the two situations. One, according to Euclid's geometry, based on obvious truths, if there be two straight lines and another straight line across them, and the angles formed thus are each equal to 90 degrees, then these two straight lines will never meet no matter how far extended. That is, they are parallel. Now let's consider the different situation. Take any two longitudinal lines of our Earth. At the equator, these longitudinal lines are straight lines along the ground, and with the equator falling across them, the angles formed are each equal to 90 degrees. Hence, as per Euclid's geometry, these two straight lines should never meet no matter how far extended along the ground. However, when these two straight lines are extended along the ground, they actually meet at the poles of the earth. Thus, the characteristic of straight lines is different when the surface on which they are drawn is curved. To take further examples, the rectangle on this ball was a normal rectangle when the ball was flat. But once the ball is inflated, the straight lines become curved lines and the angles become wider. And if you see the same rectangle inside the ball, you will find that the straight lines are curved inwards and the angles have shrunk. The very same with a triangle on a curved surface. In short, shapes and their characteristics, that is geometry, is different when the shapes are on a curved surface, whether curved outward or inward. And since the shapes have to be on a curved surface in this, it began being called curved surface geometry. Further, if you see Euclid's parallel lines shape above, the whole shape, no matter how far extended, is on one flat surface or plane, whereas every shape on a curved surface is on more than one plane. Thus, the longitudinal lines at the equator of the Earth are on a flat surface or plane at the bulge of the Earth, whereas the poles of the Earth, where the longitudinal lines meet, are on a plane behind. If their plane be imagined, then it will be through the middle and center of the Earth, like the path of a knife slicing through the middle and center of the Earth. Hence, This geometry is also called not on one plane or non-planar geometry. However, the most common name for this geometry is non-Euclidean geometry to distinguish it from Euclid's geometry. Now, what are the uses of this curved surface geometry? You will be surprised to know that most modern technologies, satellite telephony, GPS signals, the flight paths of high altitude aircrafts and missiles, etc., all have to reckon the curvatures of their own paths plus the curvature of the earth. And if you consider space, it is full of curvatures. In fact, Albert Einstein, the scientist of the previous millennium, is said to have observed that in the universe as a whole, curvature is the norm. Flat surfaces are only in those regions where gravitational pulls are low, uniform, and stable, like on Earth. And thus, the present and future is non-Euclidean geometry. So then, if the present and the future is non-Euclidean geometry, why learn Euclid's geometry today? Now, Euclid's geometry, which now began being called Euclidean geometry to distinguish it from non-Euclidean geometry, is flat surface geometry or all on one plane or planar geometry, as seen earlier with the parallel lines and can be seen here for the two Euclidean theorems reproduced. This flat surface geometry is required, firstly, for all day-to-day work concerning shapes on Earth, where we have flat surfaces. We saw many examples of such work in the first introductory video. Secondly, everyone needs to learn Euclid's geometry to learn how to demonstrate logically for all careers, even non-science and non-mathematical careers, as seen in the second introductory video. Thirdly, Euclidean geometry is needed to facilitate understanding in Cartesian geometry, trigonometry, and calculus, as seen in the previous third introductory video. And lastly, we need Euclidean geometry to serve as the base for learning non-Euclidean geometry, which as seen here evolved from Euclidean geometry. Okay, now to summarize and remember what we learned in this video. The purpose of this video was to see the third of the three types of geometry. We first noted the first two types of geometry, which we had studied in the previous video. Thereafter, we saw that the third type of geometry evolved in the 19th century AD when Carl Friedrich Gauss and others began questioning Euclid's system of geometry and found that his obvious truths were obvious truths only on flat surfaces. They were not obvious truths on curved surfaces. Shapes and their characteristics were actually different on curved surfaces, and the knowledge of shapes and their characteristics on curved surfaces became the third type of geometry. Hence, this began being called curved surface geometry. It also began being called non-planar geometry because a curved surface is not on one plane. It is on more than one plane. However, the most popular name for this geometry was non-Euclidean geometry to distinguish it from Euclid's flat surface geometry. We then saw that this third geometry has high-tech uses on Earth and in space. Accordingly, as said to be observed by Albert Einstein, this is the present and future of geometry. However, despite this, we have to first learn Euclid's geometry, which is flat surface geometry or planar geometry, and now called Euclidean geometry. We have to learn this for the four important reasons learnt. Alright, we saw in the previous video and this video the three types of geometry. Number 1, Euclidean Geometry, body of knowledge of shapes and their characteristics on flat surfaces. Number 2. Cartesian Geometry, system of expressing and analyzing algebraic equations as geometric shapes and vice versa. Number 3. Non-Euclidean Geometry, body of knowledge of shapes and their characteristics on curved surfaces. And this is the present and the future of geometry. Now you may hear of geometries with different names, but they are all combinations and or advances of these three types. But to learn and use any geometry, you have to start with Euclidean geometry. And so, with this we begin our march towards mastering Euclidean geometry from the next video. I'll see you there.